Hey guys, here's the review for Spiral 16. We're going to start off with rational exponents and radicals. First things first, we got to simplify completely with no negative exponents. I'm going to take that 1/3 and probably distribute that to everything in there. I could also start by dealing with that division, but they have to do with common denominators, and I don't want to do that at the moment. I will in a minute, but let's see what we can do first. So we're going to go 8 to the 1/3. We're going to go 3/4 times 1/3 is going to be 1/4, so x to the 1/4. And y to the 4 times 1/3, that's going to be 4/3. On the bottom, we've got y to the 1/2 times 1/3 is going to be 1/6. And then we got y to the 1/3 times 1/3 is 1/9. This is kind of making me regret that I didn't do those common denominators first. But whatever, we'll keep going from there. So the next thing I might take a look at is the bottom part of my fraction, because I've got two pieces there. And in looking at that, we've got a 1/6 and a 1/9. And if I combine those, my least common denominator is going to be 18. So that'd be 3/18 and 2/18. When I combine those in the bottom, I'm going to end up with y to the 5/18. 8 to the 1/3, that 1/3 is a cube root, so 8 to the 1/3 can be written as 2. X to the 1/4, and y to the 4/3. And finally for this part, we're looking at combining my two y's by dividing. That means I'm going to be subtracting, so we're looking at 4/3 minus 5/18. And we're looking at a common denominator of 18 again. 4/3 is going to be the same as 24/18. If I multiply top and bottom by 6, that gives me 19/18. So 2x to the 1/4, y to the 19/18. Second one of these we're going to handle in a really similar fashion. There's some less stuff going on here. Take a look at my numbers first. 8/4 is going to be 2. Then we've got x to the 3/2 minus 13/4. And, oh man, these are all x's. I didn't even notice that. Let's handle the top first, then deal with the bottom. So I'm going to erase what I just did. And it's not going to let me. Well, that's okay. So I took care of combining those two. So I might as well combine those two by doing x to the 1/2 minus -3/5. And then see what happens afterwards. This is going to be messier, but we should get to the same answer. Okay, 3/2 and 4ths, I'm going to write that as 6/4. 6 minus 13 is going to be -7/4. So x to the -7/4. And for my other guy, we're dealing with halves and fifths. That's going to be 5/10 and 6/10. 5 minus -6 is going to be x to the 11/10. All right, now I'm going to combine these by adding my exponents. So we have 2x to the -7/4 plus 11/10. My least common denominator here is going to be 20. So that's going to end up being, so times 5 is 35/20, and times 2 is going to be 22/20. When I add those up, we get 2x to the -13/20. In other words, 2/x to the 13/20. Next up, we're going to convert this to exponential notation. This is going to be c to the 2/7. The index becomes the denominator. The power becomes the numerator. Same thing for part 2. Really important thing number 1 is I need these parentheses. If these parentheses are not here, your answer is incorrect unless each piece has an exponent. My power goes on top, and my index, if I don't have anything, is a 2. It's the square root. Last piece of this to simplify, we've got 5 times the square root of 300 times square root of b times square root of c cubed. Let's take a look at this individually. Square root of 300, square root of b, square root of c cubed. Okay. 300 could be rewritten as square root of 3 times the square root of 100. I chose that because 100 is a perfect square, but I could choose to break this down in different ways. Square root of b, nothing going on. C cubed I could rewrite as c squared times the square root of c to get all 3 of those in. Now let's break these guys apart. We've got 10 here, so 5 times the square root of 3 times 10. Square root of b gets to kind of chill because we don't have anything to do. Square root of c squared technically is the absolute value of c. I'm going to write that, but if you were to just write c, that would be okay too. And the square root of c is going to hang out by itself. Finally, I'm going to write anything that's not in a square root out front. So we've got 5 times 10 times the absolute value of c would be 50 absolute value of c. Again, if you just wrote c, you'd get credit for it. And then we've got square root of 3 times square root of b times square root of c, which would end up being square root of 3bc if you reassembled that. That's about as simple as we can get. For number 3, we're dealing with some function operations. We're going to find f of g of 2, and I'm given 2 functions up above. First off, I'm going to find g of 2. And g of 2 is going to be 2 cubed minus 2, which is 6. And I'm going to take this and plug this into f. So f of 6 is going to be negative 3 times 6 plus 7, or negative 11. Next up, we've got f of m. F of m would be negative 3m plus 7. F of m would be negative 3 instead of x. I'm going to put that f of m in, negative 3m plus 7, and then plus 7. So all I did was substitute that whole thing in for x. So we get 9m minus 21 plus 7 is 9m minus 14. 5, I've got to find an inverse relation for this and decide if this is a function or not. Okay, so first off I'm going to do x is equal to y squared minus 4. To get the y by itself, I'm going to do x plus 4 is equal to y squared. And to get the y by itself, I'm going to take the square root of both sides. And I get plus or minus x plus 4 is equal to y. Sorry, plus or minus the square root of x plus 4 is equal to y. This plus or minus is going to be an issue. It's going to be an issue because if I were to try to graph this thing, I'd end up with one half that were a positive square root graph. The second half would be a negative square root graph. This would not be a function because I have 2 values for every x value, except the end there, but anytime I have even a single time that I have to decide if it's the positive or the negative that I'm looking for, then that would be an example this is not a function. All right, here we've got given a graph, sketch the inverse. So I'm going to sketch this in the same graph. 3, 0 would become 0, 3. 2, 1, that's this point, would become 1, 2. So that's here. Negative 1, negative 2 would become negative 2, negative 1. And it looks to me like we have a parabola, and it seems like I can't actually hit my points. My graph's a little bit off there. But if you were to take a look at this line of supposed symmetry here, you could see that if we flipped our imaginary paper over that line, that those two graphs should match up if you had someone more competent drawing that than I. Next up, we got to graph some radical functions. There are a couple things we have to remember here. The first is that we need some really important point, which in this case can be the end point or point of inflection, and a couple other points on this graph. You've also got to identify the domain and range as part of this. We had a general strategy here, and that strategy was to make a table. For these graphs, I'm going to look at what goes on the inside to make that 0. In this case, that would be 2. And if I plug 2 in, we get 2 minus 2 is 0. Okay, square root of 0 is 0. Negative 0 is still 0. Plus 2 is 2. So the point 2 comma 2 would be on there. I'm going to go one value up from that. And if I do that, I end up at 3. So 3 minus 2 is 1. Square root of 1 is 1. Negative 1 plus 2 is 1. Okay. If I try to go backwards, we get 0 minus 2 is negative 2. Square root of negative 2, oh, that's imaginary. That means it's not going to show up on our graphs. So for square root functions, that boundary where we hit that imaginary number is going to be our end point. It might be nice to go one number up again to see what the shape of this is. And to do that, I'm going to try to make the inside 4, take a nice perfect square, and that's going to be 6. 6 minus 2 is 4. Square root would be 2. Negative 2 plus 2 would be 0. So 1, 2, 3, 4, 5, 6, 0. My graph looks something like this. And we're done. For the next one, we've got a similar setup. I'm going to set up my axes. Oh, I forgot to do domain range. I'll go back and do both of these after I set up my graph here. XY table. This time I'm going to start at negative 2. And I get a first value of 0. When I plug that in, I'm going to go up 1 to negative 1 and down 1 to negative 3 just to check to see what happens. So negative 1 plus 2 is going to be 2. And by 2 I mean 1. Cube root would be 1. We get a fourth. Ew, that's lovely. Going backwards, we got negative 3 plus 2 is negative 1. Cube root of negative 1 is negative 1. Oh, that one works. So we can have negatives inside this one, but not inside the square root. And then times a fourth, we get negative a fourth. If I were to go up to the next time that this works, my next cube root number would be 8. So it's whatever would make this inside 8. So that'd be 6. So 6 plus 2 is 8. Cube root is 2. A quarter is a half. Still not a pleasant number, but that's okay. I'm going to make my y-axis really big so we can see this graph. And if I go backwards until I get to negative 8 on the inside, that would end up being negative 10. And looking at my values here, we end up at negative 10 and then negative a half. All right, so I'm going to make this one, that negative 1. Here's that point, negative 2 comma 0. Negative 3, negative a 4 might be somewhere like there. I might end up there, and then somewhere like here. Well, it's a terrible graph-looking thing. This one should look like a hurricane symbol. And if you are a better artist than I, or have a better stylist than I, although hopefully you'll be doing this on pen and paper instead of on your Chromebook, so that won't be an issue, then you will get a graph that looks much nicer. Okay, let's talk domain and range. For my first graph, my domain is limited. You could either do this from the equation or look at the graph to say that x has to be greater than or equal to 2. It's important that you keep in mind that that 2 point exists, so you need that equals part. The range for this would be y, and I have a maximum for y, and then I go down from there, so y would be less than or equal to 2. In interval notation, x could be, the domain could be written as 2 to infinity, and that would be a square bracket at the beginning. The range would be written as negative infinity to 2, with a square bracket at the 2 for the equals part. Again, you don't need to use interval notation, but I want you to at least feel like you've seen that when you get to pre-calculus. Okay, solve each radical equation. Oh man, this one has a fractional exponent. Whatever could I do? Well, let's start by getting this piece by itself. So maybe minus 6 to both sides. And I get x minus 2 to the 2/3 is equal to 1. Okay? I'm going to rewrite this as x minus 2 squared to the 1/3, because I happen to know that 1/3 is the same thing. Oh man, I could just convert this to a radical at the beginning. That would have been easier. Same thing as the cube root. Okay. To get rid of a cube root, I know I've got to cube both sides. And x minus 2 squared, 1 cubed is 1. And then I've got to take the square root of both sides. Square root, square root. X minus 2 is equal to plus 1, and x minus 2 is equal to minus 1. That means x equals 3 and x equals 1. Let's plug these back into the original equation to make sure they're not extraneous. Actually, I'm going to plug it in to this equation because that's before I did any squaring or square rooting, but that looks a little bit nicer. Let's see what happens. So 3 minus 2 squared to the 1/3 is equal to 1. 1 squared is 1. Cube root of 1 is 1. 3 works. 1 minus 2 squared to the 1/3 equals 1. 1 minus 2 is negative 1. Squared is positive 1. Cube root is positive 1. Nice. Both of those answers work. By the way, if you're cube rooting something and solving an equation with a cube root, you're probably not going to have extraneous solutions. Next one, let's get that cube root piece by itself. Plus 4 plus 4, negative 2 cube roots of x plus 5 is equal to negative 6. Divide both sides by negative 2. And we get x plus 5 is equal to positive 3. I'm going to cube both sides. X plus 5. And that's going to be equal to 27, which means that x is 22. Just to make sure, we get negative 2. Cube root of 22 plus 5 minus 4 equals negative 10. All right. That's going to be 27 on the inside. Cube root of 27 is 3. And if I don't know where that minus 5 came from. This should be minus 4. I got confused there. Negative 2 times 3 is negative 6. Minus 4 is negative 10. That solution works as well. We have no extraneous solutions. Now we're looking at variation graphing simple rational functions. Looking at the variation part, we're looking at the number of absences of student X is directly related to the number of days of school we've had. I'm going to call X absences and Y days of school. We know that direct variation should be Y equals KX or MX. You could also have written this as y over x is equal to k, or whatever variables that you're using. If we've had 110 days of school, okay, so 110 is equal to k. Student x has been absent 15 times. Okay, I can solve for k now. So to get that, I'm going to divide by 15. And I end up getting... both those are divisible by 5. The bottom is going to be 3. The top is going to be 22, and that's not reducible. Okay, so k is 22 over 3. So I'm going to write this as y is equal to 22 over 3x. All right. How many times will student X be absent? So that's going to be my X value in 180 days. All right. So I have the days of school here. That's 180. I want to know the days of absences. Okay, so I'm going to plug in 180 for y. 22 over 3x. And I'm going to multiply both sides by 3. Awesome. I get 540. This is a lovely set of numbers. Over 22 is equal to x. That's going to reduce into 270 over 11 is equal to x, which is somewhere on the order of 20-something-ish. The nearest one to that would be 265 is divisible by 11, so that would end up being 25-ish. All right, number 10, z is jointly related to x and y. So I could write this as z is equal to some scale factor multiplied by x and y. When x is 2, y equals 5, z equals 30. That should be a separate sentence. So we're looking at 30 is equal to k times 2 times 5. That means that k is 3 for that to work. What does z equal when x equals 5 and y equals 10? So z is equal to 3 times 5 times 12. Z is equal to 180. All right. We've got to sketch a graph of this rational function. We've got to identify any important points and asymptotes. We've got some general strategies for this. We've got to find a couple points, and we've got to take the time to identify some asymptotes. I tend to like doing asymptotes first, so I'll tackle my VA. That's going to be whatever we would do to get the bottom equal to 0. So 3x minus 1 is equal to 0. When x is 1/3, we have a vertical asymptote. I'm going to graph this over here. So if this is 1, that might be 1/3. Okay. I might go for my y-intercept next. If I plug in a really large number like 1,000, by y-intercept I mean horizontal asymptote, we end up with like 1,003 over 3,000 minus 1, which you might notice looks really similar to 1/3. Okay, so if that's my y equals 1, 1/3 would end up being my horizontal asymptote as well. Another rule of thumb, if you look at the leading coefficients, so 1 over 3, that will tell you the horizontal asymptote. Okay, what we're going to do from here is find some intercepts. Y-intercept we get by plugging in 0 for x. So I'm going to do that here. We get 0 plus 3 over 0 minus 1 equals negative 3. So 1, 2, 3. X-intercept is going to be from whatever the top is 0, because that's if we do 0 divided by that, we get a 0 as an answer. So it'd be 0 up top. So x equals negative 3 would be my x-intercept. A little bit out of it today. That would make up that side of the graph. To just confirm where my graph is on the other side, I might plug in a point like x equals 1. So if I use x equals 1, I get 1 plus 4 is going to be 1 plus 3 is 4. Nice Freudian slip there. And 3 minus 1 is going to be 2. So I get the point 1, 2 on this graph. And that gives me some nice confirmation that I should have a nice smooth, you guys call these bubble letter L's, to make sure that I have the other part of this graph in there. Okay, finally we're looking at another one of these. This one we tend to like a little bit better because the asymptotes are a little bit easier for us to see. When I have a problem set up in this format, we can pretty quickly identify the vertical and horizontal asymptotes. VA, once again, is going to be based on whatever makes that denominator equal to 0, so x equals -1. If a graph or if an equation is set up in this manner, that horizontal asymptote is going to be that term at the end. You might think about this as transformation notation, and my basic function here is going to be y is equal to a over bx minus h, and then plus k, where k is that horizontal asymptote. Whatever makes the denominator 0 is going to be my vertical asymptote, and a is the steepness of this graph. Okay. Talking about this in terms of x-intercept and y-intercept. For the x-intercepts, we've got to figure out what makes this graph equal to 0 in terms of y. So 0 is equal to 2 over x plus 1 minus 3. If I add 3 to both sides, I get 3 is equal to 2 over x plus 1. If I multiply both sides by x plus 1, we get 3x plus 3 is equal to 2. If I subtract 3 and then divide by 3, we end up with x is equal to -1/3. Okay, so that was my x-intercept when y was equal to 0. So x equals -1/3. And finally, y-intercept is going to come from when I plug in 0 for x. So we get y is equal to, and if I plug in 0, 2 over 0 plus 1 is 1, minus 3, -1. Let's sketch a graph of this guy. Do this over here. We've got a y-intercept of -1. We've got a horizontal asymptote of -3. So that's y equals -3. We've got a vertical asymptote at -1. X equals -1. And a x-intercept of -1/3. So that's going to be like right here. And that kind of makes sense for a curve that should look like this. I'm going to plug in a point to the left of the asymptote just to make sure I know where my graph is going to be. So x equals -2. -2 plus 1 minus 3. 2 over -1 is -2. Minus 3 would be -5. That'd be -2, -5. And that confirms that I should have the other half of my bubble letter L on this side.